Good evening. Welcome to our CIS 120 Week 5 web lecture. This week we're going to talk about column family databases, and then we'll do a parallel exercise that will be analogous to the individual exercises assigned for Week 5. And I hope that's useful and helpful to you. So let's talk about column family databases. These are kind of exciting because they have some of the best features of the things that we loved and have been missing in NoSQL with respect to our old relational databases. They have a lot of the same aspects. We can even find products like Cassandra that give us a very SQL-like language, which is familiar and comfortable for those of us that are accustomed to relational databases to manipulate them. At the same time, they preserve some of the underpinnings and roots of key value databases, so we can get some of the best features of key value if we organize and configure our column family databases that way, and derive a lot of those benefits as well. So they're kind of a nifty middle ground. As a matter of fact, many column family, air quotes, databases are increasingly being referred to as hybrid databases because they can be used and configured more like a column family database or more like a key value store, and so they're quite flexible. So here we're looking at your first slide from slide 1, and the interesting thing about this is we have a row ID as something very analogous to a primary key, and anytime we're talking about row-oriented records, it's starting to sound very much like a table-driven database. There are some important distinctions, and we remain schemaless, and we'll see in a moment why that is. But in a column family databases, the data is organized into columns, and it's the row ID, which is a key that's going to be based on 3 really important values that are going to help us to see something that is a little more record oriented. At the same time, by staying column oriented, what the column family databases afford us is something like the big table legacy. We can have literally tens of thousands of columns in our databases, our collections, far exceeding what we would ordinarily attempt using a traditional relational database management system. Okay, so in this view, we're getting a look into the way that we index a column family database. And the row ID is going to be indexed by a combination of a row identifier, and that's like a unique synthetic primary key. So it's arbitrary and unique, but also a column name and a timestamp. And the timestamp is very interesting because that allows us to have very easily multiple versions of the same row. And if you think about that for a moment, you can imagine, especially as we're logging web activities and that sort of thing, why it would be useful to have multiple versions. In fact, if you've done any professional work in the relational database field, one of the things that is enormously common in our tables is that we will have something called a row effective date, and we want to know when was the data originated, when was it last updated. And so we tend to add these two fields, or at least a timestamp with the row effective date to each row. And that's so common, in fact, that many products are now, relational database products are now incorporating that. And I see Melvin has joined us, so welcome, Melvin. So if you missed a couple minutes of the start here, you can go back as soon as I post the recording and take a look at that. Okay, so again, this idea of a key-driven record is, again, very reminiscent of a relational management system. All right, so let's take a look at figure 9.4. And again, reminiscent of a relational database system, the write operations are atomic. Now, remember, we've been talking about acid versus base, and the best recent relational database management systems are all about being acid, and the A in acid stands for atomic. That has to do with how quickly a transaction becomes consistent across all copies of a database. And in NoSQL, we generally are looking at eventual consistency, whereas in relational databases, we have consistency before records become available. And there are some use cases where it's really kind of problematic if we don't have consistency guaranteed across all copies of the data at once. Well, here we are with a column family database, and we can have that atomicity. And so read and write operations are atomic. So when we issue a command to update or delete or modify the data in some way, add new data, all columns that are going to be affected by that operation are written, or none are. And essentially you can think of it as a transaction rolling back. So either it's all there or it's not all there. And we don't have to worry about somebody reading outdated information. We don't have to worry about somebody simultaneously, two users, updating different parts of the same record and having a mixed result. There's going to be an order and atomicity to each transaction. One gets in first and completes, and then the second goes in, and if they're really deadlocked, then it's going to fail and roll back. All right, so figure 9.5 is talking to us about the key spaces in the key value databases, and that's what we were studying last week, our key value databases. If you think about it, the key space is analogous to the way that column families manage their collections of attributes. The difference is that the indexing is a little bit different between the two database types. So in a key value, we're going to index just on the key, and we can look up the values by the key. In the column name, we have this compound index that is going to include the column name and the timestamp linking to the value. So we're going to have actually a unique value, column name, and timestamp contributing to the index, and that's how we get that record-oriented kind of capability or dimension from the column family index. A little bit more complex, a little bit more overhead. So in terms of performance, if what we really need is a key value store, that's why we still have the key value products, as well as more hybrid products that allow us to extend the capability, use the right tool for the right job, and sometimes it's handy to have one tool that will do both jobs. Okay, so let's compare that now with a document database. So column family databases are kind of like document databases in that we can have a missing value for some columns, just like in some documents we could have missing data. So you're used to seeing our restaurants database, and you've noticed that some restaurants may not have health inspection records as yet, or some have more and some have fewer. They don't have to all be consistent in structure. Similarly, our column family database can have a missing element for any particular column value. Can be omitted. And so we maintain the idea that these are schemaless. Compare that to what we'd have to do in a relational database where the structure would have to be there. We'd have to store it as a null. So we have additional overhead to navigate and additional storage space that is required in the structure. So we pay a penalty for that level of consistency. I'm going to take just a moment because my video has disappeared of me, and I want to make sure that everything is still working here. Ah, there we go. All righty. Yeah, I'm gonna leave us right there because our next set of content, we're gonna need this video lower, so we'll just leave it right there. I've got it parked in the right place. All right, so how does a column family database store its data, and how do we navigate to it? So here is our row-oriented key, and that is going to map us not to the individual values, but to the column values for all of the columns that are participating in, that are associated with that row key. So row key A maps me to column 1 key and column 2 key and column 3 key, and column 1 key maps me to the column 1 value, and column 2 key maps me to the column 2 value, and column 3 key to the column 3 value. So you might think of this, if this maps to a map of something, it is a map of maps. Okay, so a second level of indirection, but still very efficient in terms of this index takes me to that index, takes me to the value. And of course, index lookups remain very, very efficient. So I get a lot of the performance and benefits back of a relational database system while maintaining the high performance of a NoSQL system. All right, so here's where things fall apart in terms of comparing with a relational database system. On the one hand, I don't usually need to do joins. On the other hand, you don't have that capability in a column family database. So what do we have instead? Now remember, our strategy in document-oriented databases was to try and make subdocuments out of any of the related data that we might possibly need so that we don't have to aggregate across collections. We don't have to do joins. And in the event that we do, and sometimes we may, we will have to export that data out to a Spark or a Hadoop or something in order to further process that data efficiently. And so we hit the limitations of NoSQL. In a relational database system, we would simply pay the overhead and the penalty for doing the joins, but we would have the capability to do so. So in a column family databases, instead of using joins and subqueries, the column family database is a denormalized view. And if you remember from probably the last week in your SQL class, after having learned a little bit about normalizing and deduplicating all your data, you learned about some use cases where we would intentionally go in and denormalize things. And we always did that driven by performance. And in my experience as a practitioner, at some point later, you always regretted having done that because you got faster hardware and bigger hardware, and you could have gotten the same performance and still been doing the join. And now that you've denormalized the data model, you have all kinds of kludgy workarounds that deal with that at the application level, and that's ugly. Of course, at NoSQL, the whole thing that we're trying to do is empower rapid changes at the application level because we're dealing with high velocity data and high volume data. So that's that trade-off. We've already paid that penalty. We've made that investment. So this is not a bad thing. So we use denormalization to maintain related data with a single column identifier. So here's our row ID, and remember, our row ID is going to link me to each column key for the data that I'm looking for. And so looking at this is kind of how you reconcile your multiple relationships. So you have column 1 can link you to family 4, family 2, family 3. And so we just traverse the linkages, so we can still do that very efficiently without having to pay the penalty for a join. There are going to be some situations, again, where we're going to have to do additional application level logic or processing in order to traverse data that would, in a relational database, we would have a normalized relationship for. So the care we put into our design still matters a great deal here. At the same time, we're schemaless, so we have more flexibility. So again, it's a matter of balancing the trade-offs, and in some cases we would have no alternative. If we're dealing with truly huge volumes of data, we really need a NoSQL technology. So again, the idea here, NoSQL does not replace relational database technology. It is simply another tool in our toolbox, and it addresses changes coming at a rapid pace or high volumes of data that really can't be managed well with a relational database system. All right, so here's an example of Apache HBase, and now we're talking instead of just the fact that it's a column family database, we're talking about the way that we implement the column family database at scale in a cluster. And in an HBase cluster, we have lots of specialized nodes, and the individual nodes are responsible for different functions, directing and distributing the reads and the writes, managing the regions, managing replication. All that is handled by these various specialized node types. And that's great, except you can imagine that if you are specialized, now we're back to, we've got to make a Star Trek analogy of everything. That's an IT rule, okay? And so if you're thinking about the Borg and the Federation in a battle with each other, the strength that the Borg have is everything's a cube. Everything is generalized. Every Borg ship is essentially, identical to every other Borg ship. Only scale matters, and so they're tough to defeat at that. The benefit with the Federation is, each starship is a different class. It's specialized for scientific research, or it's a warship, or they have more specialized purposes. You do get some benefit from specialization. The problem is if you take out all the warships and all that's left are the scientific exploration ships, gosh, you don't stand up against the Borg in a battle. So the HBase approach is the Federation approach. It is each node type is highly specialized. If you want safety, if you want redundancy, you then have to duplicate those node types, and in some cases, like in a master, that may be more costly or complicated or impossible to do, and so you need to worry about things like succession. If that node goes down, who steps in and takes its place, and how much latency do you have until that happens? So a little more fragile architecture when you're specialized. Let's compare that with the Cassandra approach, which is more like your Borg ship, and that is in Cassandra, every node is just like every other node, and they have peer-to-peer architecture. Everybody shares or duplicates a small amount of administrative task in order to make sure that if any node goes down, every other node is capable of filling the gap. The only thing we would need to do is if a node is temporarily down for write, okay, if we've sharded our data, so different nodes have a different partition, and if a particular node is down for a period of time, until that node can be brought back up or until it can be replaced and its data re-replicated. The interesting thing here is, just like a Borg ship, any other node is capable of caching the writes that are headed to that node until such time as they can be completed. Okay, so back to a cache architecture. Let's talk about one of the downsides, and we've talked about this before. We've done the math on why, as you grow in scale, if you have an entirely generalized, without any control on the throttle or the replication, why you start to lose to overhead. And as we count the number of nodes and then think about the number of communications that are possible, in a two-node system, one node communicates with at most one other node. Okay, so if there are two minus 1 is 1. So we're talking about an n minus 1 kind of proposition. We're also looking at how many things can I communicate with? The order is n times n minus 1, and if we can agree that for very large values of n, there's not much difference. So let's say n is 1,000. Would you agree, for the sake of argument, that 999 is not far off of 1,000? We can say, well, it's approximately equal to n. So n times n minus 1 is approximately equal to n squared. And n squared is not good efficiency at large numbers. I'm just going to take a moment and see, because I noticed that everybody shows as being muted. I want to make sure that I've enabled on the video that folks can communicate here, and that I didn't do something silly like disabling your ability to talk or to be on video if you're wanting to be. So let me.
Can you hear me, Professor
okay.
Beck? I'm Irene.
Hi, Irene. Yeah, I recognize your voice. I just want to make sure, because I hadn't heard from you or Melvin, and so I just want to make sure I hadn't locked you out and you're beating on your screens trying to be heard or seen. Okay.
I'm using a new computer, so I don't, or a different computer, so I don't know why the video is not working, but I can communicate some things.
Very good. As long as your needs are being met, then we're good. So taking a look, this kind of breaks down our n times n minus 1, or order n squared inefficiency when we have multiple nodes. So if you take a look, as we go to 3 nodes, so of 3 communicate with the other 2. 3 times 2 is 6. And then let me go ahead and turn on my pin here. Come back. So there's my pin. So 3 times 3 minus 1 is 2, equals 6 different possible communications going on here. We increase that to 4. 4 times 3 is 12. So 4 times 4 minus 1. And then 5. 5 times 4 is 20 messages. And you can see that one of the things we have, if we have a completely pure protocol, so everybody communicates with everybody else, that we soon start eating a lot of bandwidth just with our interprocess communications. So we need to find ways to tune and manage that, or we run into trouble. Okay. All right. So what about replication, and how do we make sure that our data is consistent across replicas and everybody's up to date? We learned, especially if you did the supplemental reading, about hashes in other clustered architectures, that one of the problems we had with the distribution of sharded data. So if we were going to just distribute by the alphabet, everybody who is a Wheel of Fortune fan knows that there are going to be far more entries in certain letters, STRLNE, as Vanna White would tell you, as opposed to a lot of the other letters. And poor X is sitting out there with hardly any entries at all, and so we end up with some nodes that are super busy and some nodes that are almost unused, and that's not a good balance for our performance purposes. So we used hashes to evenly distribute things. Now I'm asking you to think about hashes in the other way. So if a hash is a number that maps to distinct data, but the hashes are sparse, so the hashes are evenly distributed, we can use that property to, rather than having to mechanically go down and compare every record with every other record, if we compare our hashes and look for differences as we walk, it turns out these hashes can be represented as a binary tree. That's part of how the math works that create the hashes in the first place. We can use the numerical comparison of the hash values and very quickly say, if there's a difference, then this is different than this. We don't have to know in what way it's different. We know that it's different. We now understand there's a need, and on which nodes, of which data nodes, that is different. So what requires replication, and we can very quickly select the data elements that need to be replicated and do so very effectively without either having to walk every record and do comparison, or without having to do an excessive amount of communication in between these two replicas in order to decide, are they in sync, and if they're not in sync, what needs to be synchronized. And so that's done using the magic of hash trees. Okay. So again, one of the benefits of this sort of Borg architecture of Cassandra nodes, where it is generalized, is all nodes have information about how the cluster's running, where things are, where data is to be partitioned and written to. And that means that any individual node can, at a pinch, act as a proxy for a client. So let's say that this client wants to send a read request, but he gets serviced by node 1. Node 1 understands which node can service that request and forwards the request directly. So we don't have to talk to every node in order to find out, oh, poor client 1, he's lost in the wilderness, where do we get his data? Talk to any node, that node knows where to get it. It gets the data on his behalf. That's what a proxy means. In other words, the client isn't sent to talk to node 3. Node 1, since we've already started the conversation, talks to node 3 on client 1's behalf, gets the answer, and forwards it back. And so relatively efficient. We're only one hop away, or worse, 2 hops from end to end in getting all the response that we're looking for. And we can cache the writes if a node is individually not available for some period of time, as well as having anybody forward the read request. So pretty robust. Let's see, was there something else I was going to tell you about the Cassandra architecture? Well, if I miss it, it'll be in the reading. All right, maybe it's in the next slide. So again, if a node is unavailable, other nodes can receive the write requests on behalf and forward them to the intended node when it becomes available. So maybe it's not a matter of the node is unavailable. Maybe it's not down. Maybe it's just very, very busy. Okay. Now remember, a write request, we're not worried about when the write gets there. It's not like a read. The client, we may have to block a client if a read is not available until we can get the data. If it's not available, the client can't be satisfied without it. Here, the client is just dropping it off. He's acting as a courier. Hey, take this from me and hand it on to Martha when she comes in. And so this is the difference between going to drop something off for your friend Martha at her office where she's the CEO, and being the CEO, she's allowed to come in late, and having to wait until she comes in, or dropping it off with one of her associates, and they will see that Martha gets her package as soon as she comes in. So it's just a write. So very, very cool, very efficient in terms of allowing any to service on behalf of all. All right, that's it for the Chapter 9 slides. As always, I commend to you the Chapter 10 and Chapter 11 reading. It is not required, and I will not be writing exam questions on that material. But if you're looking for a deeper understanding, it's the way this book is organized. The first chapter gives you the overview, and the next 2 chapters give you the implementation details. All right.